Let there be carnage. I gotta tell you, so far I'm pleased with this Lennox blade. This is a variable pitch Lennox blade, and as you can see, it did a quick job of this 01 tool steel. It's a 1-inch rod. It took it 50 seconds to cut through.
Raised in court, Fulton County Superior Court Judge Robert McBurney, whose testimony has not yet issued a decision. He said he doesn't expect to rule before the November election.
800,000 people in Massachusetts are eligible to get their debt canceled. That has Senator Elizabeth Warren could reach the Supreme Court. She's confident Biden has the authority.
We've been met with these frivolous lawsuits and obstructions throughout this process, and we have persisted.
Legal experts.
Sounds recording with musicians from Indiana Avenue. Tune in this week as we explore Pharaoh Sanders' work with the jazz masters of Indiana Avenue.
Listen Thursday evening at 8 on AmazonBusiness.com. And for Fidelity, with Fidelity Income Planning, Fidelity looks at how much clients save, how much they'll need.
Leader of the Lions Den.
And tell us more about the Lions Den, because this is a group that we haven't heard much about yet.
Right. It's a renegade versions. This is more of a dynamic of a vacuum of leadership in the West Bank. And
We are going to uncharted territories. Just turned on the kiln, and we're gonna set the temperature to 802 degrees Celsius, just like that. So now the kiln is on. I spent an hour and a half yesterday trying to get the ramp and the dwell cycles properly done, because this 01 tool steel doesn't like to be heated too fast. I don't know if it leads to stress cracking or what is the failure mode, but they recommend about 222 Celsius per hour or 400 Fahrenheit per hour heating cycle. As you can see, it's still in a soft annealed state. The file is gonna cut it, and what we're gonna do is use these as test coupons and do a heat treating cycle. So first we're gonna heat it up to 802 degrees Celsius, and then we're gonna quench it in oil. So let's bake some 01 tool steel. There you go. Frying oil blend, soy and peanut, perfect for deep frying and roasting. Doesn't say anything about quenching 01 tool steel, but I think it will work. At least I'm gonna give it a try. Proper identification is the utmost importance in the workshop. Well, 3 hours later, the temperature is at 802 degrees, just as I set, and I'm the king of repurposing. This is from the fireplace, so let's see if I can make it happen. Nice and toasty. There is the piece, so let's go and quench it. These will be test specimens, just testing the waters. Got fire a little bit, not much. Let's fish them out. Part is still pretty warm, so the oil did the trick, and the oil warmed up. I'd say it's about 30 degrees Celsius. It's nice warm, but the part is still hot to touch. I can touch about 45 degrees centigrade. This is too hot to touch. So I'm just gonna let it soak there and cool down a little bit. This is how the parts look after the heat treatment and some cleaning. Just clean them with alcohol. As you can see, there's no mill scale. This 01 tool steel really stands up against the heat, so not much mill scale is generated. The surfaces seem okay. I did a hardness measurement both on the cylindrical area and on these flat surfaces. So on number 1 sample, it was 52.7, 55.9, 56.1 on the cylindrical area, and then on the flat surfaces 50.1, 47.3. You can see the little divots here where the hardness tester hit it. This is not hardness testing. This is what's called zeroing your Z. So when the CNC is coming down, you gotta find the tip of the tool, and I went a little deeper than I wanted to. Normally you put a piece of paper and you wiggle it, but you know, I'm still learning. As far as hardness, the file is gonna cut it. So whenever you see someone testing hardness with a file, it's kind of low standard testing hardness, because the file can be 62, 65 or higher hardness. Some of these files, if you drop them, they're gonna shatter because they true harden. They are like glass. And you can see in this case, this is proven that it's higher than 50 Rockwell, and yet it's cutting it. There is metal chips are being generated. So that was sample number 1. So here's sample number 2. Same thing, measured hardness right there, and on the cylindrical area it's 55 to 53.3, so mid-50s, let's say. So there's some room for improvement. And then the big learning is here's number 3. Again, measured here on a flat surface area and on the cylindrical area, and this came out 44, 46.5. Now you might remember on the video, you know, I popped the door open and then took this one out, went ahead, heat treated it, came back, you know, 45 a minute later, and then took the second one out, and in the same time the door was left open, and then went ahead, heat treated the second one, came back. So basically what could have happened is, because the door was open, the temperature, you know, it's an open air furnace basically at this point, the temperature rapidly dropped, and the temperature of this part probably wasn't an 802 degrees centigrade, but somewhat lower, and that's what caused the lower hardness. Also, this was number 3. And by the time this was heat treated, the oil heated up somewhat. Now it didn't heat up to 100 degrees centigrade. It went from 15 degrees to, let's say, 35 degrees. But you know, there's a lot for this process. You know, some people live their entire life controlling these processes in the industry, and that's what their knowledge is. And I think they have the best understanding is how sensitive these processes are, you know, for any little perturbation. And I'm not even talking about material quality. As far as it goes, this one is the softest, and the file cuts it relatively easy, and a lot of metal powder is being generated. But that day has finally arrived. The plunger or punch is ready to be heat treated. As you can see, it's O1 tool steel, so I'll have to bring up the temperature to 804 degrees, and there's a recommended rate which my controller will not be able to do, so it will reach the 804 Celsius in about 3 hours, and then I'm gonna have it soak for another half an hour. This is 1 inch diameter, so that should be adequate. So, ladies and gentlemen, please place your O1 tool steel pieces, because the doors are closing. Just like that. Let's flip that switch. See if the PID controller is in the mood. So we are at 21 degrees Celsius and we are going to 802, sorry, not 804. And I have an extra thermocouple here that I'm gonna place just to monitor what is going on. This is a data acquisition device, and we can go to record mode. So it is recording right now, and later on I can download the data and evaluate how the rate was. I'm making notes because it looks like this is not the last time I'm gonna do it, and I want to rely on my past experience. So you can see the temperature is rising. This one is at 30 degrees. That one is at 23. So we will see how fast it gets up to the 802 degree set point. We are in the austenitic phase. So let's do the quenching. I'm just gonna quench the little end, and I gotta tell you, buddy, that nucleated boiling and convective currents have never been more fascinating to me. So I'm just quenching the end. I don't want to quench the entire thing. And this upper part is essentially holding the heat, and the only thing it's cooling it is the air, while the lower part in the oil is being quenched, and I'm actually stirring the oil with it so it's cooling more rapidly. And within the metal we have heat traveling from the upper part, which is still
really hot to the lower part, which is in oil. One other way to do this would have been just to hit the end with a torch and then quench it. So by doing the 3 little samples earlier, I learned that stirring the oil with the metal helps the metal cool a little bit faster, and essentially that is going to lead to a higher hardness.
Okay, so here's where we are. I adjusted the depth of the hole so that the plunger, when it goes in, it can come out on the other side, not only to 16 millimeters, but right now it comes out around 20. And in order to limit the depth to which the plunger comes out, I don't want to use that internal shoulder. I don't want to use this shoulder. I don't want this shoulder to be like the impact when I'm impacting it, because I'm afraid that this will get stuck. Instead of doing that, what I come up with is I added a step here to the top. As you can see, this step wasn't there before, and I machined a piece of metal, a piece of pipe, and by cutting this pipe to a certain length, that is going to limit how far this guy can travel. And so I did a quick stack up here. I've done a quick stack up, so these are all the dimensions that goes into that stack up, and the length of the pipe came out at 44. So right now I have about a 1/10 of a millimeter press fit between these two. So I'm going to press them together, and then I'm going to finalize the length of this end, and hopefully that will give me the desired size or dimension for the plunger.
I am making engine parts. I cannot believe that. So these are going to be the slugs or Tappet blanks, 8620 steel, cut to size 32 millimeters. All of them cut to length, and then the ends are turned, and I put a little chamfer on it, just break the edge. And the next thing is cut this pocket on the CNC lathe, so that will be the blank basically that will be forged.
Well, that blank is completed now. As you can see, I got 5 pieces. Took me some doing with the CNC and the G-code, mainly because I was cutting a 1/4 inch slot with a 1/4 inch end mill, and that's not how CNCs work. So I had to be creative with my tool paths. Also, this interpolation on the bottom, when it's going in a XZ plane like that. The tool is moving inside like that. That interpolation flipped the circle. So anyways, just one of the things I had to deal with. As far as dimensions, you can see the width of the slot should be there you go. The width of the slot should be 15.5, 1548. I'll take it. The depth, and this is not the right way to measure it, should be 16.5. Obviously this guy has a flat at the end, so it's not touching the circle properly. And then the width is 654. So when it's cutting and it's filled with chips, it's not gonna do a 635 or 1/4 inch slot. It's gonna be wider. We live in a real world and the tool is just following the physics. Next thing is heat these up and try to forge them. This is gonna be the first batch I make for testing purposes. Well, here's the result of the first test. I'm not calling it an utter failure. Maybe it's half a failure. Essentially, it created a time bomb. So I got a slug on the lower part here, which was heated up to 900 degrees. And I got the upper part. There's a spring. So the spring right now is compressed. But as you can see, there's a gap between the press and the top of the tool. And so what essentially happened is I pressed the tool into the slug and well, it shrunk on it. And that was one of my fears essentially from the beginning. I was afraid that if this process takes too long, then the part is going to cool down and shrink onto the plunger, and that's what exactly happened. And that's why I wanted to use the hammer method, but first I thought I'd give a chance to the hydraulic press method. I got 4 more parts toasting there, which they'll have to wait for their turn. I had to resort to the good old Bridgeport to separate the pieces. This is scale from the puck, and you can see there's more here. So this is the lower tool part. When I was trying to insert the hot component, it basically got stuck halfway in and didn't go in, and this diameter inside I left about 1/10 of a millimeter. I think on one of the videos I talk about it, that it ought to be looser. And as you can see, the spring is still compressed, so there's energy stored in the spring, and this guy is basically welded on stiff. I think I'll have to go and cut it off with a cutoff wheel or something of that nature without damaging the tool. I'm not sure how I'm gonna do that, but that's where I am right now. Again, it's not a failure, it's just a little bump in the road. After some close combat, I managed to remove the lower tool section, and then by loosening these bolts here, the cap and the spring came off, and I managed to do that in an orderly manner. As you can see, the forged piece is still at the tip of the tool, and what I can tell you is it bowed out on both sides, just as I was anticipating. It didn't crack through here. That's also good. But I should have used some kind of surface agent, some kind of oil or lard or grease or something that would help with the removal process, and it has to be a lot swifter. So it should just go in and out in a couple seconds, because otherwise this guy is gonna cool so fast that it's gonna basically cool on a tool. Maybe the problem is I only have 2 degrees of taper. Maybe it needs to be more. Maybe it needs to be 5 degrees for forging. I'll have to go and consult my literature about it.